opportunity to discuss some research which I have with multiple collaborators here. Mike Barnett, who's recently graduated from University of Chicago on his way to Arizona State. Buzz Brock with his really peculiar spelling of William, but I apologize. My co-author will have to forgive me on that, but a very distinguished scholar in economic dynamics for many decades now. So what I want to do today is explore kind of some tools. I want to import some tools from asset pricing to think about problems of social relevance and to think about it from the perspective of society and not necessarily from the perspective of investors inside markets. The problem which I've chosen to discuss has to do with climate change. It's one of which I think it's quite clear there's lots of uncertainty. It's one of which there's been lots of discussion about policy implications, so it's certainly socially relevant. Now, in terms of uncertainty, I'm going to appeal to some climate scientists. This comes from a paper by Allen, and it has an et al. There with many other climate scientists, co-authors as well. And I just want to kind of, within that community, they know well that there's uncertainty attached to some of their predictions, and ones that are of critical importance to economists. The eventual equilibrium global mean temperature associated with a given stabilization level of greenhouse concentration remains uncertain. This complicates the stabilization targets to avoid 10 dangerous levels of global warming. So I'm going to adopt an approach here. In order to make any headway on this problem, I have to adopt some conceptual simplifications. And so let me tell you what I'm going to do here, and we can discuss about the aspects of which this has some naive components to it, but aspects that I also find revealing. I'm going to posit a social planner decision problem. Why do I do that here? In contrast to lots of econometric type work, here we want to explore consequences of misspecification, consequences of uncertainty, and kind of the so what of it. And to do the so what of it, I need to have a formal way to think about that. And so for that, I'm going to be using a formal decision problem. Now, in this problem, there's two interacting dynamic channels, both of which face uncertainty. So first we have economic activity. For example, CO2 emissions. They alter the climate, say temperature. This can play out over, that transmission can play out over many time periods, many decades and the like, and it's going to be very persistent. But there's also uncertainty attached to it. Now, at the same time, temperature changes. That climate change is going to alter economic opportunities in the future. Economies will have to adapt. They'll have to incur certain social costs as well. And so we start off with human activity affecting the climate itself affecting future economic activities. That can also play out in dynamic ways, and there's very clear uncertainties attached to how we think about economic damages. What I want to do here, and this is in contrast with much of the other literature in this area, is to adopt a broad notion of uncertainty with multiple layers. I want to go beyond what we think about as the risk model that we typically teach in economic classes. When we talk about finance, we talk about risk premia, risk compensations. When we talk about decision making in microeconomics, it's about risk aversion and the consequences of it. I want to push uncertainty beyond the more narrow defined confines of risk, and I'll elaborate subsequently. I want to explore how the broader notion of uncertainty operates between these two channels. Now, I'm going to follow previous literature by going after things like the social cost of carbon. And roughly speaking, this is a marginal rate of substitution between consumption and say, emissions, but done from a social standpoint, not from the standpoint of private investors. If we kind of go back to the taxation literature, this is the equivalent of trying to do so-called Pigovian tax rates. Now, where asset pricing is going to come into play is I want to interpret that kind of externality, which is as kind of a social asset, and there's going to be trajectory of so-called kind of social consequences, and I'm going to use asset pricing methods to kind of represent the valuation of that, embracing uncertainty. So what asset pricing has been good for, in part, is it confronts uncertainty. It necessarily confronts uncertainty. That's kind of figure out compensations for uncertainty. What that is, kind of what that field's all about. In macroeconomics, a lot of the macroeconomic models we use, uncertainty arguably plays a pretty second-order role. For this particular social problem, I think it's really critical to put it out in the forefront. And these asset pricing tools are going to help me think about it. So, why asset pricing? So I kind of mentioned one, is that it allows me to embrace uncertainty. And in asset pricing, that's about market compensations for being exposed to uncertainty. Okay? And then what it does then is, imagine you've got some cash flow, it pays out compensations over different horizons. Equity prices reflect those cash flows of, say, enterprises and current and future time periods, and then you deduce the corresponding valuation of those. Typical asset pricing valuation. Now, where we're going to deviate from that is that we're going to do social valuation rather than private valuation. And this is where I will have to draw upon this social objective function. I'm going to think about climate change as following. The climate change is going to be in response to human activity. That's going to play out over time, and then as those changes have consequences for societal damages or induced by economic activities. Put these two things together, kind of so-called convolutum or the like. Put the two things together. There's important interactions for those, and that's going to play the counterpart to a cash flow that shows up in these in kind of asset pricing calculations. But here, from the standpoint of from the social standpoint, and here from the standpoint of using, thinking about the counterpart to the cash flow as these kind of societal damages. So, as I indicated, there's two sources of uncertainty here. The climate side, the consequences of CO2 emissions. There's been much work in the climate sciences that analyzes this. And then, economic consequences of climate change. There's been some work in economics about this. I think much less so than from the climate science counterpart, the so-called damage representations. Now, observations. The measurement or quantification research in geophysics focuses on the first. Now, and economics on the latter. Each is dynamic. Now, here's a case where we just can't be empiricists. In fact, we're going to draw on geophysics in part because we're potentially pushing the world into situations where we have very little historical evidence. So we really have to rely on some type of fundamental structure, in this case, structure coming from geophysics. I think the same is largely true in economics. There have been empirical stats at this, at measurement of damages. I'll talk about one of those. But I also think this is a case where so-called structural econometric modeling is really at a premium. Now, what's going to happen is these two sources of uncertainty here are not, in some sense, going to be additive. We just can't add them together. There's an interaction between them. They're really going to have a multiplicative character, in the sense that when both happen to be small, their product is going to be really tiny, and if when both happen to be large, their product is going to be huge. They can amplify one another. And that interaction between these two pieces, which is important. So we can't just like compartmentalize this problem and then add together the consequences. The interaction turns out to be important in the calculations that interest me. So I'm going to adopt a really very, very simple representation of climate here, just for the purposes of this talk, for the purposes of some initial calculations. We're in collaboration with climate scientists to do more ambitious versions of all of this, and then we're trying to work through the computational challenges that go along with that. But this is going to draw an approximation that actually comes out of the climate science literature. It's not one that we are making out. It's one that we're able to extract from that literature. I think about it going back to Matthews, but there's been subsequent work on this as well. And here's how it works. There's a whole bunch of different climate models out there. These climate models can be highly complex. It can sometimes be very, very challenging to even solve. They have ambitions beyond the ambitions of our work here in the sense that they look at geographical impacts as well as dynamic impacts. There's a lot of spatial interactions and the like. They're potentially rich models, but they're also they're highly nonlinear models, they're borderline chaotic models, and they're challenging to solve. We just can't take some complex climate model, stick it inside an economic model, and do anything practical. That's just not possible. So we have to deal with some type of approximation. Climate scientists are fully aware of this as well. And so what Matthews and others have noted is the following. They'll take simulations from these models, okay, or variations in initial conditions or going across models, and then they'll look at the output of those simulations. And then they'll tabulate responses over long horizons in terms of emissions. So they'll try to see how things like temperature respond to emissions over various horizons, including ones that are long. Now here I have to be a little bit clear on what I mean by long. I mean long from the standpoint of economists. Long from the standpoint of geophysicists is, of course, in a completely different manner. They'll simulate their model out for centuries and centuries. And I've had a long history in doing economic time series, and if we make it for a few decades with some reliability, we're doing pretty well. So we're not going to. So we're going to do long from the standpoint of economists, not geophysicists. So for them, it's much more modest time scales. Okay, and that's kind of where this approximation is meant to work. If you crank it out further, over centuries, it's going to start breaking down. And so this is a rough approximation, but it's an approximation that seems works remarkably well across simulations. There's been multiple studies that document its performance. And for us to get started, it's a very nice starting point because it means basically, if we take emissions, think about emissions today as have, roughly speaking, a permanent consequences on temperature. Now, as I say, if you play this out over centuries, they're not going to be permanent, but they're going to be highly persistent. And then we'll boil down to thinking about this kind of climate sensitivity coefficient, this beta sub f. That beta sub f is going to tell you what you emit today, what the long-term consequences are on temperature changes. Okay? And so we're able to, at least to exploit this Matthews style approximation in order to get this, boil this down to a single coefficient. Now, of course, this is way too simple, and as I say, we're in collaboration with other geophysicists to do things that are somewhat more ambitious. But the quality of this approximation has been assessed across multiple studies. So roughly speaking, the emissions today, for our purposes, has a permanent consequences on temperature, and this beta f is this kind of temperature sensitivity parameter. Okay? So now there's this parameter that I can go to climate sciences and try to figure out what it tells us about it. So here's a histogram that comes out of a very recent paper by McDougall and co-authors. It tabulates the heterogeneity in this parameter across different models or across different initial conditions. So what you see here is a blue histogram, and that's just a tabulation of the model heterogeneity or the initial condition heterogeneity as well across these models. And you can see it's actually quite substantial. There's lots of variation. We just fit, and this is going to simplify our calculations, although we could do them more ambitiously. We just fit a normal approximation to it, just for the sake of simplicity here. But it gives us characterizations of uncertainty that we can draw on from climate science that we can then use in assessing consequences in our economic framework. So this is climate science has lots of evidence of a human imprint on the environment, but in terms of the dynamic transmissions, there's uncertainty in terms of its magnitude. And this is a compact summary of that uncertainty. So climate scientists, some of them based a little bit on skepticism of how much economists can add to all this discussion, sometimes use this approximation as an input into so-called carbon budgeting. how would this work? Well, if I think of this Matthews approximation as being a pretty good approximation, then I can say, how much of a temperature change would I want to tolerate before I kind of burn up the globe, or before there's enormous damages? I announce that budget, that carbon budget, and then I design policies in order to meet that carbon budget. And so this is kind of a way to think about climate policy making. And then we can avoid this idea of solving explicit models in some sense. But very much this is like, from a social perspective, imposing a hoteling-like constraint on emissions. So what Harold Hotelling's famous work was about exhaustible resource pricing and the like. But here, the constraint is being posed by a so-called carbon budgeting. Right. Now, carbon budgeting sounds a nice, wonderful simplification. There is an issue of what temperature threshold you might want to announce. It's kind of a dramatic nonlinear damage specification. But notice that with this plot here, that the mapping between emissions to temperature change has uncertainty. So you don't really know what budget constraint to impose because you have to confront this. So even with the simplification, uncertainty is very much on the table. You can't. It doesn't allow you to sidestep or duck the uncertain component of it. Now you could say in the dynamic setup, what could happen is the fact, well, okay, I don't know now, but I'm going to observe the actual temperature changes, and I can kind of make adaptations as I get closer and closer to the threshold, and turn it as a fully dynamic problem. To do that, then, one would indeed have to go back to some serious model solutions as well. But it's not routine to just simply announce a carbon budget, given the uncertainty that's coming out of these climate science models. And in fact, we're going to take it further. We're going to add on economic structure in order to help guide this and explore so-called damages that aren't quite as extreme as nothing happens until you hit a threshold and then the world burns up. So I'm going to just give you a picture of the model which we're looking at, and then I'm going to spare you the equations, though the equations are critical for our solutions, of course. But let me try to describe it with this diagram and in words. So this is going to be a very simple model. The thing we're going to abstract from here, and it's a very important abstraction, which we certainly want to extend in the future, is any type of geographic, distributional effects, between warm climates and cool climates, climate economies and the like. So we're going to think about this as a world economy for the moment, and this follows some other literature by Nordhaus and others. So we're thinking about this. There's going to be capital here, okay? And it's going to be a so-called AK type model with capital, except there's going to be adjustment costs. Okay, so capital is going to have output. Output's going to be divided into three components here. Direct consumption is going to enter in preferences, exploration, and then investment. And then investment plugs back to the capital stock subject to adjustment costs. Now we put in this channel here that most of the literature doesn't do, but I actually think it's actually quite important. This is this reserve channel and exploration. Historically, the hoteling model isn't really, reserves have not been getting, in some sense, measured reserves have not been getting depleted in any very serious way over time. New discoveries happen and the like, and so we can't just impose a Harold hoteling constraint on this. It really with much credibility. So instead, we're putting this, we're putting this model, which is trade-offs between the efforts you put on investment, exploration, and consumption. And then there's this kind of curvature between the exploration and the reserve augmentation. Then from reserves, you draw down reserves, emissions. And these emissions can go straight into preferences as one model. They can say you may have this preference for leading, because damages, some form of damages are going to enter preferences, and you may have preferences for economy without dramatic temperature changes, or it can be scaling output here. It can be scaling output in the economy in kind of adverse ways, which is quite difficult in the literature. Where the third mechanism is going to be impacting growth rates. Okay, so I'm going to skip the formal mathematics here. It's going to be convenient for us to do this model in continuous time because of some of the pricing consequences. That means we're going to be building in these kind of Brownian increment shocks, these locally normal shocks. This stuff can be done with jumps. It can be done in discrete time as well. But our initial calculations are in this Brownian. Is in this kind of local normal setup. Let's see. So I'm going to skip this. This is a lot of. This is a formal statement of the underlying economic economy. I've described it for you in words. This is the reserve evolution. As I say, this is an important component of our model. Hoteling becomes a special case of this, and we set parameters to certain extremes. Okay, so we're going to be looking at 3 different specifications of so-called damages. So there's going to be this mapping from temperature changes to economic damages. One is this preference mechanism I talked about, which is the way we've designed it is pretty much computationally equivalent to adverse impact on production possibilities. It's kind of a one-to-one map in the computations. Not in the measurements, but in the computations. So our model solutions can be kind of reinterpreted as kind of either one of these two. And that allows us to make some connections to the economics literature. The third specification is in growth. So instead of having climate be damaging productivity possibilities, some have argued that its impact is going to be on growth, and that's going to have adverse consequences on growth. So we also explore specifications with that feature to it. Okay, here's the so-called damage specification. I'm not going to. This is kind of a key part of the mapping that goes from the climate to from the climate side back to the economic side. Let me talk a little bit about this one. This is where the negative externalities come into play. Now, this specification we're borrowing largely, or roughly speaking, from the literature, and there's a lot buried in this. In principle, one would want to put adaptation inside the economic model and work out optimal responses to climate change going forward. And that ought to be part of the damage specification. That's a gap in the modeling. It's not a gap in just our modeling. It's kind of a big gap in the whole literature, and it's one that would be great to close. There's going to be this gamma. There are these gamma parameters that have to do with the mapping from emissions into the mapping from temperature changes into and economic damages. There's going to be parameters here. There's going to be kind of a gamma 1 and a gamma 2 parameter. This gamma 2 parameter is going to be our source of a nonlinear damage adjustment. Some of the literature, typically the literature has forms of nonlinearity. I'll give you graphical depictions of those subsequently. Now we're going to add on to this type of specification an additional penalty that's going to be a smooth counterpart to a carbon budget. And it's also going to allow us to get at some of the aspects that Marty Weissman's been arguing for within the context of this literature. We're also going to design this to have certain forms of coefficient uncertainty, the random coefficient type model in terms of the way that we've designed our Brownian increments here. But the key part of this is the fact there's going to be a multiplication. Remember, the beta sub f parameter is a climate sensitivity parameter. The gamma parameters are the damage parameters, which we have to extract from the economic side of things. Okay. What shows up here is an interaction. The beta sub f's multiplying the gammas. So that's the sense of which uncertainty here is kind of multiplicative and not just additive. And that's important in our calculations. So that's the evolution for log damages. Then, of course, the level of damages has a counterpart to it. Okay. So damages and preferences, as I say this, we may equivalently think about this as a model with kind of proportional damages to consumption and or production. So we'll just enter them into preferences. We're going to have log preferences, and then we look at kind of log C minus log D here. And then we've got this term coming from emissions. So this is one specification to consider. Damage to growth, then it's the capital evolution. K here is capital. The capital evolution, the key thing here, all the log stuff is the adjustment cost. The key thing here is a log BT term. That says that damages are diminishing the growth rate in the capital stock. From the standpoint of the private sector or private individuals, that's exogenous. From the standpoint of society, then it's not. So this is This is our alternative specification here. So I talked before about measurement challenges. So there's really little historical evidence to draw upon. We can't just be empiricists here. There's not. There's only so far one can go with that. Impacts are likely to be different for different regions of the world. They're differentially exposed to climate. That's something we put off the table, but it is pertinent to some of the evidence we talk about. And my co-author Buzz Brock has been doing work that explicitly confronts regional heterogeneity. Potentially, then, there's big differences between short-run and long-run consequences because of adaptation from the economic side, which is, this particular specification is kind of off the table, but I think potentially is, from a quantification side, probably should be on the table. So here's the first type of specification of damages. We're going to lift out specifications from two proponents of damage functions, Nordhaus and Weissman. Think of these as proportional reductions in say, output, if you like, but it can be terms over the laws of these determined preferences. The Nordhaus one takes a very kind of more benign view of what the potential damages are as we crank out temperature changes relative to the pre-industrial counterparts. And so that some of this Nordhaus work is based on survey evidence from asking other experts. Damages are something that we don't know a lot about, so I'm not sure I have some skepticism about just asking experts, but anyway, that's the Nordhaus specification. So think about that as one possible model of damages. This other one is our approximation to a Weissman specification, and that's given by the blue line. So roughly speaking, up until temperature change 2, these two are tracking each other. So the range of temperature changes we're in now, these damage functions are the same. Where they differ is you start pushing it off into the tail, under which the Weissman one has more severe, implies more severe consequences. Think about a climate budget as equivalent of drawing a vertical line somewhere. Here I just drew it at the point at which Weissman and Nordhaus basically start converging, but one could draw it at other points as well. And so one could imitate carbon budgets by taking that blue curve and putting more and more curvature into it, and kind of getting away to its blue rate. Now, Weissman talks about uncertainty to motivate a specification. So my calculation, what I'm going to do is I'm going to take Weissman a little bit worse, and that's going to be the dashed line, and then allow for weighted averages between Nordhaus and Weissman. We're going to call it Nordhaus and Weissman here. That is, we don't know which model is correct of damages, and we're going to confront it as a situation where we're uncertain what the right view of the world is, what the right economic view of the world is in terms of damages. So this is going to be an important source of uncertainty here. So here we've got uncertainty about how to weight these two different models, and then we also have uncertainty about coming from the climate side, and these two are interacting on us. So when we solve out our model, what I'm going to do is I'm going to put on the table multiple components of uncertainty. And let me just see something. You should close your eyes for a second. The slides are out of order. Let me talk about this slide. When we solve the model, we want to take into account three components to uncertainty. The first is risk. So we're drawing on insights that people often attribute this to Frank Knight. Frank Knight wrote this rather interesting book on risk, uncertainty, and profit. It's a very heavily cited book. I'm sure if you do Google sites, you'll find a whole bunch of them. Frank Knight talks about these issues in his book. I think very few people really read it because it's not the most coherent discussion of these issues, even though these issues are on the table. But so he's certainly wrestling with these, way back in the early to mid 1900s. About the same point in time, or close to that time, Keynes is writing treatises of probability, trying to push us away from standard probability theory based on concerns about uncertainty. So in some sense, we're trying to deliver on some of Knight's distinctions, although I wouldn't want to push that too hard because I'm not sure exactly what Knight had in mind. So risk is the thing that we talk about typically. I want to talk about risk as a situation in which you don't know outcomes, but you know probabilities. Okay, so I often teach risk aversion in economics classes. We write down probability distributions, but its outcomes we don't know. So that's the risk aversion model. Okay, now I want to draw another distinction: ambiguity, uncertainty across models. So we've got these multiple models on the table. I don't know what weights to attach to the possible models. So this is a piece that statistics discipline has wrestled with for decades. And one can think about people like Finetti and Savage as giving an elegant treatment of subjective probability, all motivated by this question. And both Finetti and Savage were very clear. Savage himself in his own decision model thought it was only applicable in very, very simple situations. And both say that these kind of subjective probabilistic inputs are things that we often know only incompletely. So there's a sense in which we want to do a counterpart to robust prior analysis. I might put priors across these models. This is a situation where you don't learn your way out of, very quickly, and so its uncertainty turns out to be very, very, very durable. So we think about this as not knowing what prior to put and doing some type of prior sensitivity in some formal way. Now there's going to be misspecification. Okay, this is uncertainty about models, or unknown flaws of approximating models. So the models we write down in economics, it's true in climate science too, are wrong. We know they're wrong. They're simplifications or abstractions. If they were a complete description of reality, they would be pretty much useless. So the question is, how do you use models in sensible ways? So this is the hardest one to wrestle with. It's truly a challenge. We take a stab at doing it, and this may well be the most important source of uncertainty, but conceptually the most challenging. So we're going to explore how these different components impact social planner problems, and how they impact things like a so-called stochastic discount factor. So like in finance, when we do risk adjustments to cash flows, it's best to think about those as stochastic discounts. Sometimes in social valuation, there's always debates about what is the discount factor. In an uncertain environment, it's not really a well-posed question, because depending upon how you're exposed to uncertainty, will not be differentially discounting things. And so, and so these treatments of uncertainty interplay with kind of how this discounting works. Now, how we're going to proceed is how we're going to navigate through all these components of uncertainty. So, these statistical models are specified. We may have ambiguity of which one is the best and like. Robust approaches, their aim is to use models in sensible ways, but to still use probability and statistics, not just toss it out and give up on probabilities. I think that would be far too extreme reaction. We're going to impose uncertainty aversion. That is a dislike for uncertainty about probabilities over future events. So just like risk aversion is a theory of caution. It induces people into more cautious behavior. The same is true of our broader notion of uncertainty aversion. It's going to be a theory of caution. A little bit different theory. Sometimes it looks like risk aversion, sometimes not. Now the outcome of this is, as you go across these components for your uncertainty, you're going to be looking at the ones that are most consequential to the decision maker. This is where the decision problem is critical here, because for me to ask pose the question, does uncertainty matter? Matter for what? And that's where the decision problem comes into play. And let me just emphasize, if you talk to non-economists and start talking about we don't know things, they think the next step is therefore we shouldn't do anything. Decision theory of this type does not say you don't do things. It does not say inaction. In fact, it says you embrace that uncertainty and make the appropriate adjustments. Okay, let me just see. So there's a couple approaches to decision theory. These are just like advertisements of stuff. There are multiple literatures on this. I get to draw on literatures from the economics from economists' contributions to decision theory. My collaborators and I have made some contributions to these, especially trying to work out continuous time counterparts to them. And there's different approaches to these, to proceeding along these lines, and these are just some references to those approaches. For today's talk, I'm going to be primarily working on the stuff that I've done with Meow recently, trying to implement some ideas of Klebanov-Marinacci and Mukherjee. And I want to think about this in situations in which there's uncertainty about priors we might want to put across models, and making additional adjustments for model misspecification. Okay, so now my slides are out of order. I want to go back to the previous order here. Actually, one more thing. So we want to do the social cost of carbon as an asset price. I'm going to take this social planner problem that has these different components of uncertainty built into it, forms of uncertainty aversion, and I'm going to take that and I'm going to take the solution to that and reinterpret it as an asset price. Asset pricing is stochastic, but here we have to take the asset pricing and modify it for concerns about ambiguity and model misspecification. So in asset pricing, people often use this trick of so-called risk-neutral probabilities to absorb all the risk aversion into prices. Here we're going to be doing a little bit of a counterpart to that. We're taking out this ambiguity adjustment, or this model misspecification adjustment, mapping it into a probabilistic type adjustment, and then using kind of more standard calculus associated with asset pricing. We're going to then be computing shadow prices and efficient allocations. And these are allocations which are not necessarily observed in competitive markets. So as we do asset pricing, it's not going to say, it's not going to open the door that I can go read all the inputs from my looking at competitive markets because we're not because presumably we don't want to presume that we're in a socially efficient allocation right now. Otherwise, we could do exactly that. I should also say that the social cost of carbon here is a nice simplification for our computations. From practical purposes, I think it's pie in the sky. I don't really think that all the world economies are going to agree to implement some carbon tax or going to implement some common cost of carbon. But I think even if you want to think about questions about subsidizing green energies or other potential approaches to climate science, uncertainty is going to be important. These same type of tools are going to be relevant to those problems. Okay. Now I'm going to go back to the earlier slides. Sorry about the misspecification. Okay. So I'm going to first do this kind of this kind of level damage specification. We put a couple models on the table here. We don't know how to weight them. We know I've already told you the uncertainty coming from the climate side, from the so-called McDougall plot. Okay, so here's and the way this works is that, as I indicated, is that part of solving the model is you work out these kind of worst case PDFs. And if these are pertinent for pricing, they're pertinent for kind of how to produce the cautious solution. So what I've got here is the original normal approximation to this climate science parameter. And then I've got this yellow thing, this yellow curve that shifts it to the right. The shifting to the right is this cautious adjustment we're making for not knowing how to weight these two different models. Say the more benign model of damages versus a much more extreme model of damages. We began with weighting 50-50 and then proceed. Now this is done at baseline numbers. Now at the baseline numbers, we're in that region where the two models coincide. So therefore, this probabilistic adjustment you make is going to be identical, just because the two models in play are not. You're in a region where they're not yet operative. Now they're operative in the decision problem because I want to explore all possible alternatives, but it's not operative at the allocations which we're computing here at year 0. If you play this out for say 100 years, you start getting some divergence into the two different pictures. Oops. And here you see it. Here's the green. Here's the original blue curve, but now I've got two curves. One is the low damage curve, the one that I labeled Nordhaus, and the other is the high damage curve, the one that's motivated by some of Weissman's work. And then you see under the high. Now you're seeing dependence here. In fact, the shift is bigger for the high damage specification than the low damage specification as part of this computation here. So part of the adjustment is these shifts in these probability densities here, into more conservative positions, and you've done the equivalent of shifting the damage density damage densities to the right as a cautious adjustment. This isn't what the decision maker believes. These are calculations the decision maker does to deliver a form of aversion. And as I say, it's the same one that's pertinent for state valuation. So part of the story is these density shifts. The other part is there's two models on the table. We start off 50-50, and on this particular set of calculations, you take the 50-50 and you re-weight it about 1/4 towards the low damage regime and 3/4 towards the high damage regime. And so those adjustments come out as well. So how you weight the kind of yellow versus red starts also gets shifted here as part of the calculation. Now, again, this is 100 years at what you observed, and remember, this is the socially optimal trajectory here. So you've designed social policies so that emissions aren't quite so dramatic. In the decision problem, the decision maker has to consider much more scenarios with much more dramatic adjustments, and those adjustments would show up much more prominently here in terms of part of that solution. So here's like outcomes of this particular specification. If we had ambiguity and neutrality, here's the emissions trajectory, and under this ambiguity aversion, then it comes down, and rather substantially so. And that's just kind of captured by this, by these trajectories. Now these are models that start punishing in a really high way big movement, large amounts of extractions of emissions. So they have a hoteling-like feature to them. And so that's what's kind of delivering this downward specification of the emissions trajectory. There's a sense in which qualitatively this is behaving like a hoteling model qualitatively. We also have social cost of carbon calculations, and so that's what these are. And so this is the kind of pricing counterpart on the hoteling, and we expect those to increase. And in the hoteling model, literally exponentially. So I have multiple lines here. This is a kind of a decomposition of this price, of this social price here. If I ignore the externality, I would have that black at the very bottom. That's kind of labeled private. That's a component as if you ignore the externality completely. Okay, and the cost there would be kind of trivial. The next line gets you the uncertainty adjustment per se, and that's the fact that I have this theory of caution, and I have to make those adjustments in my valuation formula. The red line then captures the externality, okay, and then I kind of combine these. Then I combine these effects, and then I get the social cost of carbon. The key thing to me in this plot here is that blue line is making a non-trivial adjustment, and the adjustment's getting bigger over time. And that's in part what's supporting this decay in the emissions rate as we go forward over time. So these are the type of calculations that I think are useful. I think it's very useful to try to explore. We can change these aversion parameters. We can change the inputs. We can change the damage specifications. But I think these type of calculations are valuable because they actually show you in a meaningful way how uncertainty affects the outcome of the decision problems. And so part of what we're really about is developing these computational tools more generally to confront this uncertainty in the broadest of terms. So now let me turn to growth rate damages. And here I'm not going to show you the computations. We have some, but they're not quite ready for prime time yet. But let me just show you some damage uncertainties here. So the way that some researchers have looked at growth rate damages, this goes back to some work by Dell and Ilkin, but it's been built on by many others. So look across countries, okay? And to look at how growth rates respond to temperature, in part, not just dynamically, but cross-sectionally. Now here, you're living a little bit dangerously because you want to think that warm climates have different growth trajectories than colder climates like North America just because of damages, or is that proxy for something else? So it's a very, very big concern here that you're exaggerating the impacts here of say, temperature changes. The models they fit literally have fixed effects in them, and so they try to make some adjustments there, but I think it's not at all clear that they capture things. So they're trying to look at cross-sectionally to figure out how the dynamics are going to play out. It's interesting. I think it's maybe a stretch to push it very far, but we thought it was useful to do some of the calculations. So we took some evidence from Burke, who's doing these type of studies, and then I'm just quantifying the different quintiles of the damage function. These are growth rate damages, and then these are the different quintiles that come out of it. To show you, to kind of characterize the nature of uncertainty coming out of this evidence. First of all, these are fairly severe damages, but there's also a fair degree of uncertainty about them as well. So we can now input these type of Burke probabilistic statements, specifications, into our calculations, and then proceed with the corresponding set of calculations like I just showed you. In this case, drawing on this growth rate evidence. So I'm not necessarily a full advocate of this evidence, but the evidence can plug into our calculations in a pretty much straightforward fashion. And here I'm expecting our calculations to show even more dramatic consequences of climate change because of the growth project specification. So anyway, as I said, what we're all about here is kind of developing a toolkit that allows us to confront these different forms of uncertainty. So these are what we talked about, and they go forward. So where do we stand in this? I want to wrap up here. The social cost of carbon can be can increase substantially by broadening broader notions of uncertainty. And I gave you a graph that illustrates that effect. There's an important interaction between damage uncertainty and climate uncertainty. Remember some of those densities I had were already involved. We're showing differences depending on whether you position on the high damage or the low damage type scenarios. And indeed, those would have played out in bigger ways as we explore the tails of the damage specification. Now, of course, there's lots of extensions that are needed here. We're trying to ramp up our computations to be able to explore them. We're engaged climate scientists with more ambitious climate model inputs. We want to assess other potential policies. This social cost of carbon is a convenient computational device, is a convenient laboratory for our calculations. As a pragmatic policy recommendation, I guess I have my doubts. It's the political economy that seems rather complex. We also want to compare climate damage uncertainty with other sources of growth uncertainty. For instance, technological uncertainty. And economic historians like Gordon and Mulcair, they debate about the prospects of technological growth going forward. Gordon is very cautious, says over the last century in the U.S. we had this amazing era, don't expect it to continue, and people like Mulcair said no, that's the wrong view of the future, that there's going to be wonderful opportunities coming forward. We want to confront that as a situation, again, with uncertainty going forward, as a different source of uncertainty. And then these tools are going to allow us to do comparisons between the magnitude of that uncertainty comparable to this one, more or less. And those type of calculations we view as potentially very important. Anyway, that's where we want to head. In conclusion, decision theory under a broad umbrella of uncertainty does not imply an action, but yet I do find it a very useful framework to do sensitivity analyses. Asset pricing and decision theory tools help us in navigating through multiple layers of uncertainty. And climate science, I think, is a very good, climate economics is a good example where these multiple layers come into play. Thank you very much for your time.